like this. Probably this guy. Oh, exactly 500. Is this on or no, Professor? Professor, so here I please let me introduce you first. So,
do you need a mic?
One statement. Good evening, everyone. Welcome to the another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Emina Soljanin, and she will be speaking on codes for unexpected loads. Emina is a distinguished professor of electrical and computer engineering at Rutgers. Before moving to Rutgers in Jan 2016, she was a distinguished member of technical staff for 21 years in various incarnations of the Mathematical Sciences Research Center of Bell Labs. Her interests and expertise are broad and currently range from distributed computing to quantum information science. She is an IEEE fellow, an outstanding alumnus of Texas A&M School of Engineering, the 2011 Padovani Lecturer, a 2016-17 Distinguished Lecturer, and the 2019 IEEE Information Society's President. In 2023, Emina received IEEE Information Theory Society Aaron D. Weiner Distinguished Service Award and Miss Urmila Agarwal Distinguished Visiting Chair Professorship at the Indian Institute of Sciences. We request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. Feel free to unmute yourself and ask directly or type them in the chat box and we will relay your questions. Over to you, Professor.
Thank you. Thank you very much for inviting me to speak here and to visit here. I'm very happy, and this is already my second week and everything is going well, knock on wood. And especially this program is very meaningful for me because it was given by someone who is honoring his mother, and it's for more senior people, women, right? So I'm going to talk about these codes for unexpected loads. And this cartoon here, I guess it's unexpected, but at some point I hope it will become clear why it's there. And let's see. I am not able to move this, but that's all right, I can. It did work before. Yes, let me check if this is working. Okay, it is, all right, thank you. So I worked on various aspects of this problem with many people. The bald-faced person here is my student who worked with me on the technical part of what I'm going to say, but I'll cover much more. And we have an NSF award, and also this ICERM funding. This is also a mathematical institute at Brown University, and this WISDM is Women in Data Science and Mathematics. To look like wisdom, they put it Science of Data and Mathematics. where we met twice with subset of some of these people and talk about some aspects of the problem. So what I'm going to consider is distributed, what we call service model, where I have n servers providing service to multiple concurrent users. And that could be cloud nodes, edge nodes, and they can provide streaming or download or computing. That could be service. For us, it's going to be storage most of the time. And just think about going to buy something, and various stores are providing opportunities for different people to buy different things, and some stores will maybe sell only milk and some only bread or something like that, rice. And so we distinguish between two functional components at each node. One concerns storage, so there is some disks there, and the other service, also for request processing. So this is, if you look at the analogy of a store, this would be like having people communicating with you, giving you the stuff that you want to buy, and also they have their storage room from which they take what you want to buy. And that will be defined more precisely mathematically within a few slides, but just think about storing, for example, data object A and data object B, and also data object A plus B, and various people arriving and queuing to download A or B or A plus B. For what purpose, we'll see later. So here n is 3, and there are two data objects that are stored redundantly. So first we look into what is the storage model here. So we will have k equal size data objects, and they're stored on n servers, and k is smaller than n. And data object is represented as an element of a finite field, some fq. We will have a bunch of examples where this field is just a binary field. And the coded objects are linear combinations of these data objects over the same field. And each server in this model that I'm going to address, it only stores a single object, whether it's coded or the object in the clear itself. So here is an example. I have 3 objects, A, B, and C, and then I'm storing them as A, B, and C, but also as A plus B, A plus C, B plus C, and A plus B plus C. And they are listed in this order not only for the picture to look nice, but also if you look at this is 1 and 2 binary strings, 3, 4, and so on up to 7. And what we see here is that someone can download A by downloading only A, or can download B and A plus B. And when we have a group of objects that, group of servers that provide jointly a download of an object, we call that a recovery group for that object. We'll again define it more precisely. And here for A, we have these recovery sets, RA1 to RA4. RA1 is a little bit special because it's just the data object itself. And so that's for the storage model. For the service model, there are 2. One is bandwidth, which usually wireless people like more, and one is queuing model, right, which some people here work. I met with some students of Parimal who told me about their work. The bandwidth model, we assume that the server has some bandwidth W and can accommodate mu users at the same time. And for the bandwidth model, we assume that the rate of service, like average rate per unit time, is some mu, right? And this will mathematically turn to be identical for us, but it's just easier to think sometimes in terms of one versus the other. And then requests for object I come at some rate lambda I. If it's bandwidth model, we think about that as lambda I users want to be present at the same time in the system, want to occupy bandwidths of these cumulative nodes. And for the queuing model, it's just the rate of arrival, which queuing people you know that rate of arrival should be smaller than the rate of departure from a store, not for a queue to grow outside of the store, right? And when we put all that together, there are arrivals here for just this one object, lambda I, which I can then split and allocate a portion to the systematic node itself, and then another portion, which I call portion 2 or allocation 2, which I will allocate to B and A plus B jointly, because I need all these people to download from both to be able to decode, right? And if I have a request, a lambda A, or this is a load or unexpected load, then this lambda A1, 2, 3, and 4 is the request allocation. Okay, so which request vectors, lambda A, B, and C, can be served by a system if I have it storing data in a particular way? It's what we are going to be spending some time analyzing. When we started, this problem was some queues which turned out to be complex to analyze. And these are queues to coded storage. And then we realized that, that even finding out when these queues are stable is not an easy problem. And that's how this problem grew. As we worked more and more and chatted with people around about the problem, everyone was telling us, oh, this generalizes batch codes, or this generalizes codes with locality availability, locally recoverable codes, right? And so sometimes they also talk about that, but since lots of work on distributed storage has been done in this institute, especially in Professor Vijay Kumar's group, and also Sasha has done some fundamental work in this area, I thought I'll just tell you a little bit why this is different. So if I'm storing data A, B, A plus B, and A minus B, then I can ask you how many recovery sets there are for A. Question. Answers accepted. Expected. So I can recover A from A. I can also recover A from B and A plus B. Anything else? B and A minus B, and also A plus B and A minus B. Now, in the recovery set, in the this notion of locally recoverable codes, we want these things not to overlap. So we have choices, but we usually don't want them to overlap. So there would be only 2 sets that we can use. And let's consider here a bandwidth model that 6 people can fit, 6 users can fit here. I can send 6 here. And I can send also another 6 both to B and A plus B, and I can simultaneously serve 12. However, if I look at the model that I just described to you, I can serve all, I can actually combine them. They don't need to be disjoint, right? And so since they don't need to be disjoint, I can do some other kind of combinatorics. And I'm still sending here 6, but I'm also sending 3 here, 3 here. So I'm using all these 3 groups other than, in addition to the systematic that you mentioned to me. So that would be the difference. And we'll come back to this a little bit. Again, this is not essential for this talk, but since this particular audience may be more familiar with LRCs than an arbitrary audience, I'm going to mention that. The rigorous formulation of the problem is the following. We want to find this set of vectors, lambda 1, lambda 2, and lambda k, that can be served by a system. And lambda I is the request or demand or load, right, that's offered to the system by requests lambda I for object I. And the lambda ij are allocations or portions that go to the J3 pair group. And so what we want to do is, so now each node, as you have seen in the previous slide, will be getting a load from requests from different users, even different requests from a single user. Here I only have a user. So therefore, I have to ensure that each node does not get a request in excess of its capacity, its service rate, its service rate. So this is what this first constraint is about. And of course, to say that I can serve lambda 1 to lambda k, I have to ensure that when I sum over all portions for each lambda j, sum over all portions that are served by different repair groups, that they sum to this lambda a, lambda j, lambda I, whatever. And if you look at request allocation that is integers, then you have something called integral service rate. And some of you may recognize an instance of a batch code in such scenarios. And so here is an example. So this is going to be a set of all such lambdas is going to be a convex polytope. That's not easy to show. In fact, this is sort of a linear program, except that it has potentially exponentially many constraints. So I cannot, even if I wanted to, just feeding it in a computer is not always easy. So now here is an example. If I only store ABC, it would be this kind of a shaded box inside. That would be my service rate region. These are all loads that I can serve. If I add another node and put a C here, then nothing will change in the life of A's and B's, but C will get more options. If I put as a third node B plus C, then again, nothing will change for A, but B and C will have more options. And now if I put A plus B plus C, then all of them will have more options. So all of these turn out to have the same volume, which is not always the case, but they cover different skews in of the popularity of these objects. And we look in a little bit about how to derive that. So to just recap what I told you, this is my, I just described one problem, but there are actually a few more. So again, k data objects are stored redundantly across n nodes. Data objects are represented by elements of some field. Each server stores a linear combination of data objects over that field, and requests for object I arrive at rate lambda I, and each node requests are serviced at rate mu, which I'm going to assume to be 1. So it's going to be normalized. It's going to be 1. So most of the time you're going to spend looking into determining these rates once a code is given. But as coding theorists, our number one task is to design a redundancy scheme in order to maximize or shape the service rate region. When someone tells us, in your system, these are going to be demands, how should my code look like? Right. And the last is to evaluate the performance. Now you have designed a code, maybe you can express the service rate region, but these lambdas are their expected rates, but even the expectations vary, right, in systems. So some demands may spill over, so you want to see how many. So for these two, I'll talk a little bit at the end just to give you a bigger general picture. So now, before I get into mathematics, where some of you may decide to check out, let me just give you another example from real life. Suppose that, I don't know how real life it is, but anyway, there are two movies, A and B, and three cinemas, and each cinema has 100 seats. So you can think about that as the bandwidth model, right? You can pack 100 people in each. But you know that lambda A people want to see movie A, and lambda B people want to see this movie B, performance B. And the only thing you know is that these cinemas are in a city or in a region where only 200 people go to see movies, right? So you don't know how many will want to see A. And since there are 200 of them, maybe all would like to see A. So you can say, okay, I'll put A maybe in the last one also, or do something so that I can accommodate to put A in 2 and B in the last one. But what if that changes? So what do you do? So yes, in the first one, you can put A, say Aladdin here. And in the second one, you can put B, Beauty and the Beast. And what do you do with the third? And the answer is you will put A plus B in the third, right? That's actually the right thing to do. But then whoever wants, if there are 100 people who want to see A, then you're fine. But what if there are 150 who want to see A and only 50 B? So the first 100 for A, they're fine. They're in this first cinema. The 50 people who want to see B, they're in the second cinema. They're fine. But these other 50 seats can be occupied by people who want to see A. However, in addition, they will also want to see A plus B or download to their phone so that they can exert those two movies. And there is some cost associated with it. So that's also another question. Yes, you can serve this, but there is a cost associated with it. So which vectors lambda A, lambda B are possible? So let me now talk a little bit more mathematics, and then we'll come back to some more general stuff at the end. Are there any questions about the model? No? All right. So so coding theory is like, yes.
Allocation will depend on the lambdas. You know the lambdas. Is that correct?
Okay, so that's a good question. So if I give you a vector of lambdas, then there may or may not be allocations to meet that. There may be multiple allocations to meet that. And I want to find all lambdas for which I can do that. And yes, allocations will depend on lambda. Now, suppose someone tells me lambdas that are, they cannot tell me the entire regions, but he said, you know, like with this, I have 200 people and, you know, I don't know them or something. How would you design this region? So that is going on. But the short answer is yes.
The other question related to this is, usually you had a picture of a queue, which means that these arrivals are asynchronous. They could come at their own time and leave after service. So I was wondering if there is a study of that aspect as well, dynamic aspect of the queue.
So this is just they are arriving at this average rate. This average rate has to be smaller when you add them over everyone who arrives at that node, smaller than the service rate. So that's for stability. However, there is a synchronicity aspect, for which I have two slides to address. And I've been talking a little bit with Lolita about it. So here, I just thought W as a letter is not important. It's just within that W, I can put mu people. So, for example, here is, I don't know, 50 meters, but so that would be W. But the only thing I care about is how many chairs get into each row. So if I stay with 50 meters, like the airlines usually do, but then, you know, want to squeeze people a little bit more, that would influence what the mu is.
So there's a service rate of mu for each server.
So in the queuing model, there is a service rate mu. In the bandwidth model, the number of people I can pack simultaneously, let me go back to that picture, that I can pack simultaneously is mu. Because I assumed I assumed a little width here, something. If I make this narrower, it can be some other mu. Does that answer your, anyone else?
So you say allocation. So one allocation is just that how do I divide arrival into different servers? Like given test towards something. And you mean that you give me a sequence of arrival and I will tell you what should I store in different nodes so that I can meet this arrival.
Exactly, these are two questions, yes.
You will answer those.
I'm going to address the first one a little bit more. I don't know, we'll see how many questions come and things like that. So when a coding scheme is given, we have, we know all the lambdas that we can handle for the simplex code and a class of MDS codes. And I will talk a little bit about that. For the other, I'll just mention some general things. I'm not even sure how much I will cover from the first, but my goal is to, for you to understand the model and mathematics that gets into it, which is fun, or relevance also for engineers, for the system. And I'm here until the end of the month, so whoever wants to talk a little more, we can talk. Anyone else? Uh-huh. No. No. Within the group it has, because if I send 5 people to download B who want A, then those same 5 people have to download. All right, all right. I was thinking across the groups. Within the group, yes, absolutely. It will come when I start solving it. Yeah. Maybe he was asking, let me check. This, lambda ij are connected to a group. So this is lambda ij's portion assigned to the group. So the entire group, each node in a group gets that. This way?
Yeah, so lambda AP, for example, like this, going to 4 and 5, same way.
Anyone else? Okay. So,
one more question. Is there an assumption that the only data in a particular server is A or A plus B or?
for this talk, and actually we didn't even do much more than that. We said there is only one data object per node. Yeah. But let me just flash this model again. Yeah. Each server stores a linear combination, which may be an object itself of an object. Okay. So, right. So, coding theorists like to deal with generator matrices, parity check matrices, but actually the only thing that matters here is collection of vectors. That's why I call this collection of storage specifying columns. And this column, the numbers in this column are the coefficients that I will use to make a linear combination. And for people who are more in mathematics, occasionally this ghost will appear, and you can also look at that as point in the projective space. So here is an example. So this matrix here for the simplex code, I just list all strings of length 3. And I start, I list them numerically. So it's 1, 2, 3. If you look at this numerically, it would be 1, 2, 3 up to 7. And encoding would be multiplying CBA by this G, which will produce this code word or this set of objects, coded objects that I should store. Another example is this other class that I will address if time allows, is this MDS codes, and the first one is canonical. Again, someone will call this a rational curve. And the other one is a systematic MDS code. So these are these matrices that I have, and the columns are important. So what are minimal recovery sets? If I take a subset R of columns in G, I call it a minimal recovery set if A is in the span of R, and S, but A is not in any proper in the span of any proper subset of R. So you cannot remove any vector and hope to recover A. So here, These are the minimal recovery sets of size 2 for object A. There are some minimal recovery sets of size 3, but actually for this particular code, we don't have to use them. You've seen that we had to use them in one example to get the maximum. Here we don't. I'll talk a little bit more later about that. So, for MDS codes, again, these are the recovery sets. This is just, instead of what we were just talking about, said in a different way, and they don't have to be disjoint. So you can get 1, 0 by XORing these two, or by solving these sets of linear equations. So these are all recovery sets. And now I'm going to define something that we call recovery graph. So there are many graphs associated with codes, different graphs, right? And here there is something called the recovery graph. And I'm going to define it for matrix 2 by n, or it holds also for other matrices which have recovery sets of size 2. If that's not the case, then it wouldn't be a graph, but a hypergraph. And the extension is straightforward. We'll see it a little bit later. But let's just understand this concept when we have 2 by n generator matrix, like we just had for the other. So what I'm going to do, those columns that I called your attention on, these are going to be my nodes. And whenever, so this is, to define a graph, I need to define a set of nodes and set of edges. Edges I'm going to define as based on the recovery sets. So whenever 2 nodes, and I said recovery sets are of size 2, whenever 2 nodes are a recovery set for some object, then I will put an edge and also label that edge by that object. Right. So for example, and I'm going also in systematic case to add 2 nodes. Right. So for example, this is my G here. I'm going to have nodes 1, 0, this is my first column, 0, 1, this is my second column, and third and fourth column. Now, from the last 2 columns, I can recover either E1 or E2. For these 2 columns, I can recover only E2 because E1 would not be if I want to recover E1 from these 2, this would not be a minimal recovery set. So for each systematic, I add something like this kind of additional node. So this is how the graph is defined, right? And when I have, anyway, any questions here, how the graph is defined? This is a tool. So it's a definition. Just hope it's clear. There is nothing to understand or, yeah. Okay. So here is an example when recovery sets are 2, but K is not 2. So this graph is actually bipartite. So on one side, I have all columns which have odd weight, and on the other side, all columns that have even weight. And this is bipartite because I cannot XOR 2 columns on this side of the identical parity and hope to get something which has parity 1, because I'm recovering EIs, right? So these are not going to be connected, and the same on this side. That's the same argument. So it's a bipartite graph for this code, and in general for simplex codes. I'll talk about them more. Now, there is another way to draw this bipartite graph as this triangle. So 5 is this 101 node, for example. And the reason to draw it in this triangle is because there is an associated finite geometry, it's called Fano plane, to this code. So lines and points, each one of these is a point, and each line along a line, or a hyperplane in this case, if I XOR everything, I get a 0. So what this has to do with this? Well, if I look at the independent set of, largest independent set of this graph, it turns out to be a complement of the points included in this hyperplane, which is special because it does not contain any elements of the standard basis. So it's not essential for the talk, but I just want to call your attention that there is a geometry part and a combinatorics part, and among my collaborators, some people like geometry more. This talk is going to be more combinatorial and algebraic. Okay, so in order to talk about, what do I need these graphs for? Well, I need them because understanding fractional matchings on these graphs is going to be essential for me to derive these capacity rate regions. And when I say matching, usually people think about bipartite matching. They think about bipartite graphs, and bipartite matching would be a set of edges that connects left nodes to the right nodes, and these edges don't have a node in common. So it's usually what people know. And various things like marriage theorem and some such things are based on the matching problem. But here I'm going to have not a bipartite, but a general fractional matching, which some people would define as a function. We are going here to define it as a vector. And that vector is going to have as many components as there are edges in the graph. And to each edge in the graph, I'm going to associate a real number in such a way, in order to call it matching. When I look at each node, these numbers have to sum to something which is smaller or equal to 1. Right. And that's a fractional matching definition. Right. So now we define lambda JW to be the service rate for EJ in matching W as the sum of all weights in the matching that are labeled by EGW. So let me actually immediately go to an example. So if you remember, our graph consisted nodes were corresponding to the columns. Edges connected two nodes if these two nodes form a repair group. The first label is saying which data object I can recover by accessing these two nodes. The second is a number. All of these purple things, the second numbers, are a valid matching, because if you look at them and look at the sum of whatever goes in either of the nodes, it will never be larger than 1. Right? So this is a matching. How does this matching matter for lambdas? So this matching is the allocation. Right? How do I get from an allocation to a service rate for EJ? I sum everything that has a label EJ. So here E1 is here, has a matching component associated to it 1. E1 component associated to it 0.5 and 0.5, and another 1.5. So 3 0.5s here. And 1, that will give me 2.5 for lambda 1. And lambda 2, everything is 0, so no service for lambda 2. So is this clear, the association between, so the matching would be an allocation. Any matching is an allocation. But then when I map that vector, which has a dimension E, into a vector that has a dimension K, in the way that I just described, that actually collects everything that has a label EI into one number, then I get the service. So a service vector and its matchings. So there is something we call a greedy matching, and that is when you see what your lambda is, 1.5, and then you put as much as you can in your allocation to the systematic nodes. So in that sense, greedy. So you put 0.75, everything you can put to the systematic node. Everything else, E2 is then 0. And then here, I cannot put more than 1 because it's a matching. So I put 1 here to the systematic node, and then try to see if I can get another 0.5. I can from here. And this is another way to get same numbers. So two different allocations. So there was a question. Do allocations depend on matchings? Yes, and vice versa. And two different allocations will give you the same matching. And there will be a theorem later. I'm not sure if I'll cover it or we'll take some other way. Is that it says whenever you have a matching for a certain vector of lambdas, there is also a greedy matching for this MDS codes. Yes, Parim. So for me, just now I want to find the stability. So this service rate region. But there are some drawbacks of greedy matching, yes, that we don't even understand. So tell about that later. Yes.
Why is it called a greedy matching?
Because you greedily want to put everything on the systematic. It's not, it's our term. If anyone thinks about better term, please tell me. Yeah. So, anyone else? Okay. The set of all fractional matchings on any graph is called the matching polytope. In fact, if it's fractional, we call it fractional matching polytope. And the set of all service vectors is called the service rate region. And so this service rate region is an image of the fractional matching. But then the fractional matching, you may say it's really hard to find this first polytope and now you want an image of it. It turns out that in some cases, you don't really have to know the fractional matching polytope in order to know the service rate region. And you can answer actually a number of other questions. So our problem is find all these lambdas such that in R to the K, such that there exists a matching in the matching polytope that yields this lambda I. So that means that here I don't have to find all these matchings. I have to only find out that there is one matching for this to say that this is in the service rate. So how does one specify a polytope? You can specify it as an intersection of hyperplanes, but you can also specify it by telling what its vertices are. That's another way, and we'll use both. And here, for this particular graph, the service rate region is the intersection of these hyperplanes that are written here, plus the lambda 1 greater than 0 and lambda 2 greater than 0. So this is the service rate region. So now you can actually compare, you can make some bounds about the service rate region and compare coding schemes based on these bounds. So you don't always have to find, although we are curious, to find these regions. So for the picture before, which is the service polytope, is this red thing, there is something we call maximal achievable simplex, and that is something that we know within this simplex. Simplex structures are sum of all lambda I smaller than something. That's a standard simplex. Plus positive, right? So this maximal achievable simplex is something for which we know that our service polytope is within that. It could be multidimensional, right? Something we call, sorry, that was maximal matching simplex. Maximal achievable simplex is something that we know we can achieve. And it's very often easier to find than the entire polytope. We are only looking for a simplex that is within it. And so the polytope is inside this. And here, just for a reference, I've drawn LRC simplex, which, remember, the LRCs are only interested in these points that are axis intercepts. And if I have two codes, and I know that maximal matching simplex of one is within the maximal achievable simplex on the other, then I know that polytope, because one is below here, another is there, I know that polytope is included in the other one. So we can use that to compare. Okay, so now in the interest of time, I'm going to skip some of these, how we find these things. There is something called matching number. In the integral case, it's even hard, for hypergraphs, it's even hard to find, even when the size of an edge is 3. So anyway, there are ways to find with lots of work, of course. And they contain these, I don't know how much people are familiar, matching number, vertex cover number, etc. But in any case, there is some mathematics behind that. So for the binary simplex code, this is the one that has a bipartite graph. Here things are easier, except that you have to prove that the graph is indeed bipartite and that it has a certain structure. In other words, that you really don't need recovery sets of size 3, even though they may be minimal. So you have to prove that, yeah, your recovery graph, that you have to prove this structure. Once when you do that, then it turns out that the polytope of the simplex code is a simplex itself, but in the real numbers. So what is a simplex code? Maybe I wasn't clear there. Its matrix, generator matrix consists of all columns of all strings of length k. Our example was all strings of length 3. Okay, so achievability is some kind of a splitting of these rates. And the converse is based on these fractional matching numbers, vertex cover, etc. Another class of codes for which we can find these, we can characterize and compare this region is class of MDS matrices that look like this. The first one is that canonical rational Normal curve or van der Monde matrix, something that does not have zeros. And then for each I, and I goes from 0 to 1, I replaced I columns by EJ standard basis vectors. So this is that class of code. So in the simplex code, each recovery set has size 2. Here, each recovery set is going to be either size 1 or size 4. Size k, and that helps. In any case, these graphs are not graphs anymore, but hypergraphs, and we call them k-uniform because quasi-uniform because each edge is either size k or size m. M is 1 in our case. They have not been studied, especially their polytopes, but we can derive various things about this. And for example, for these 3, so this is the one with no zeros at the top. Then the first vector becomes systematic, and then the second becomes systematic, and this region grows. And each following region is the superset of the previous. And I can show that only by looking at those simplices. I don't have to derive these regions even. So this is a theorem. For any n and k, the region really grows as I increase number of systematic. So the systematic would be the best. Can we completely characterize these polytopes? The answer is yes. Whenever n is greater than 2k, we can. When n is smaller than 2k, then in some cases we can. And there are lots of things that I'm going to skip now, and I have them here just in the case people want to talk about that. And here is the turtle mystery. These polytopes for a 6-3 code, for example, look like, the first one is a simplex, and then you grow to something that reminded us of a turtle. And student Altan Kilic in the Netherlands who was drawing this was also using some kind of a green color. So then that's the turtle, like this here. Shape looks a little bit like that. And then for, if you increase n and keep the same k, I cannot draw below 3 dimensions, it still becomes a turtle but flattens out a lot. Then there are various things that you can say about when n is smaller than 2k, but I'm going to skip. And just to remind you before I say a few words about these other two problems, I want to remind you what I said, what we did so far. Again, in this model, K-data objects are stored redundantly across n nodes. Data objects are represented, are elements of some field. On each server stores a linear combination, and there are these arrival rates. We want to see if we can serve them, right? We want to find all combinations that we can serve. Right? And because what we have done, we know that there are some codes which can be simplex, MDS, these are standard classes. We also have some results for these maximally recoverable codes because they also have some of this recovery group size structure that we can say something about. But ultimate goal is to design a redundancy scheme and then evaluate the performance in practice. So I'll just, to conclude the talk, say a few words about these other problems. So someone asked about synchronicity, right? And when you look at something this neat, you probably don't think about the synchronism. But this is one of these books, and there is even a program on Netflix, how to arrange things. And these people are advising sorting according to colors, right? But then what happens? These are some snacks. What happens if you eat 3 snacks that are red? Now you have a hole there. And when you go to a store, you'll buy more red snacks, so it's easy to see. That's fine. But what if a friend comes and brings you some blue snacks? Are you going to throw them away because there is no space here, or you're going to put them in a red shelf, right? So in other words, if some of these things change, how do you need to redesign everything? Of course, if you spend some red and get some more blue, maybe you would, you need to put all of this out and then redesign the system so that colors are matched. And so here I'm just going to give you an example. There is something called asynchronous batch codes, and the name came from this paper by Riad, Skacek, and Thomas. I think a year or two there was a journal paper. I heard a little bit about that before from the authors when they have the conference paper. And they were for batch codes, well, another class of codes. We're asking what if some of the users leave, can they be replaced by others? So they're asynchronously leaving the system. So what's happening here is this is your recovery graph. And suppose that the point that you want to serve is 1, 3. You know, for simplex codes, we just derived it, that 1 plus 3, that anything that's smaller than 4, cumulative demands that are smaller than 4, no matter how they're split between users, can be served. So we know that 1, 3 can be served, and this is one way to serve it. This is what a batch code would do for you. It would tell you, read 1 from A, and for the B people, read 1. Not in so many words, because it's just equivalence, not the same terminology. Read 1 from B, another one from B plus C and C, and then A plus B and A plus C. So now A leaves from here. If A leaves and C comes, there is nothing you can do unless you rearrange everything. Whereas over here, if A leaves, it actually left the entire system in its original shape, except that its capacity is now 1/4. So the C can do whatever C would do if it found an empty system, but the rate it can get is 1/4, which when you sum over 4 edges would be 1. So there is, so we don't understand that. We haven't worked with that. We chatted a little bit with Lolita. Yeah. So if some users leave the system, can other use the freed resources? Would your capacity go down? And so that's one open question. Another is cost. This is again just a sketch. I told you here, look, I can handle various demands here. Each one of them can go up to 2, provided that no one else is using the system. And that's true, but for that, and this is a cost of downloading C. If C is up to 1, your cost is 1. You're only accessing the C node. But as soon as you want a little bit more of C, or more C users arrive, they have to access A, B, and A plus B plus C. So their cost would go at a higher rate and a little bit less here, right? And if you just replicate C, nothing would change. C would be happy. But then again, the others may not be happy, so you have to. So this is another question. How do you find trade-off? Then you can also say, well, you know, maybe there is some code over there that people are using for other purposes, and I want to see its service rate properties. But in general, and actually I talked at WinLab to more industry, people from industry, and said actually people want to say, how do I store my data? Or if you remember that pantry organization, how do you organize my pantry so that when I cook, things are accessible, right? So you start from there, not, oh, someone organized it, what can I do? Yeah, that you do when you go to someone else's house, maybe your mom's house, and you cannot move anything, you do whatever it's there. But if you can organize it based on your needs, then you would do something else. So here, these points are given. You know that lambda A is going to alpha, lambda B is going maximum up to beta, and then the sum of lambda A and lambda B will not be more than gamma, because that's how, this is your cumulative number of users. It looks like this trapezoidal kind of structure. And one can also tell you, you know, I don't want to use some high field. I just want to XOR at most, right? Or I don't want to buy some fancy containers for my pantry. I just want to do something simple. So how many nodes do I need? Or how many shelves do I need, right? So, so we can solve this for this simple case. So we will replicate A some number of times, B some number of times, and also replicate A plus B some number of times with the purpose of minimizing everything. That doesn't have to be a unique goal. I can say, well, here is your space, or here are your disks. You can use any field you want, but please keep it as small as possible. So that's another thing. You're given n, you want to find the smallest field. Or you're given the field, and you want to find the smallest n, as this was the case here. Plus, of course, you're given the points. That's your goal to cover. Here, for this particular one, we see that things change as alpha, beta, and gamma change. In the first one, we need 6 nodes. A is replicated twice, B is replicated twice, and A plus B is replicated twice. As alpha, I'm keeping beta and gamma constant, but alpha is going down. And then here, I still need 6 nodes. I still need 6 nodes, but I don't need a coding node, which is also a plus. Right? The less coding I have, the easier, the less the cost would be once when I download. Another thing I can ask is what I just said. Someone gives me a number of servers. Which points can I cover, or what would be the smallest field? We are definitely stuck there. But one thing is just to observe that from coding theory point of view, these 2 codes would be identical, but they have different regions. One is this blue, another is. So here, this replication is this square. But then if you use this one with no zeros, like canonical Reed-Solomon, you would have half of this. Doesn't do anything for you. This one does something. You know, it handles better these skews in popularity. And for a while, we thought, oh, this is the only thing coding can do, right? Handle better these skews. But because very rarely are you do you have demands that are simultaneously high for both? But then we found is that this combination of replication and coding will actually sometimes result even in the largest volume, not only extend individual demands, serving option, but also have the larger volume. Another problem is asking if I have, say, 3 systems, and mu, which we normalize to 1, several systems, but one consists, for one, n is 3, and each mu is 8, so my cumulative bandwidth, if you will, is 24. And then the other system has 4 servers, and mu is 6, so the cumulative bandwidth is again 24. So that would be the equal footing to compare them. And in the first one, I can have a replication scheme AAB, ABB, or ABA plus B. In the second one, I can have complete replication, or I can have an MDS code. And what I did here, this was my back of the envelope computation on something numerical, Desmos, whatever, just to see how these things look like. Here I generated these blue and red dots randomly according to these distributions, right? And the reason to take 4 and 8 was somehow to imitate a little popularity or whatever. And so when you see, when you ask how much is covered by any of these systems, any one of these replications, AAB and ABB, will cover 0.73%, 0.74%. And then the MDS one would cover 0.9434. So whatever you design, if someone gives you maybe some of these points, your demands, because these are also random variables, can go beyond that. Like someone estimated that they would be happy with 0 and 2, and when one is 0 and the other 2.5, they're happy. But all of that can actually, you don't know until you observe what happens in the system. So these are a few things. And the slide that I want to leave you with is that new applications, what is code for unexpected loads? Like new applications create new performance metrics for codes and new needs for coding schemes, right? Because that's in general the best way we know how to deal with uncertainty. So coding theory has been declared dead many times, but there is no better way to address uncertainty. And so what I have here is this could be some edge system, 2 cameras, one is collecting object A, another object B, and popularity of requesting what one camera is showing versus what the other can change during the time. So I often show here like a tunnel, lanes for the tunnel in New York City to go to Manhattan. So you would have in the morning people getting in, and in the afternoon most of the people will be getting out. So they redesign these lanes, right? So what you do today in the system, you would move data from one place to another. So now would be A's are more popular and then B's are more popular. But in the time of big data, you cannot just move that around, right, that much. So it's better to have some other way to provide flexibility. And here, if you have AA and BB, again, it would be this square. But if you know that for some other reason A is more popular, then you would go with this one, AA, B, A plus B, which would be the red thing here. And then again, if they're never both popular, maybe you would go with this one. So, in any case, there are a number of different questions. And of course, I'll be happy to discuss anything now or during my stay in any of these problems. And yes, I skipped some technical things, but even have a talk with more technical slides, but that would have to be discussed one-on-one, I guess.
Let's all thank the speaker. Thanks a lot, Professor, for a wonderful talk. Audience, feel free to ask questions if any.
That we didn't actually look into. This is just the ones I said, let me do just this, just as my sanity check. So I don't know really beyond this whether that's in general true. So that's an open problem.
Yeah, the second two types of the same thing can probably be achieved by doing sort of fragmentation, right? So you don't store like A, B, maybe store like part of half of A and half of B, that gives you more diversity, right?
And so now one has to be careful about that because in this bandwidth model, I talked with a number of people about that. They had, they would ask that question. It's just that then when I talked with them, I realized that this concept of bandwidth is not, kind of internalized. That whether you have half object or two objects or whatever, you still are occupying, if 4 people want something, whether that something is small or large, it doesn't matter. They have to be plugged in there. That's then another component, right? So they will stay there more, so you don't have to see how things are changing in time. And how would it decrease, right? If I have many people, like, let's say again in a store, buying, we talked a little bit about that in another paper for another topic. One person goes to buy milk and another person goes to buy rice. And now this person is buying 2 liters and the other one is buying 2 kilos as opposed to 1 kilo and 1 liter. You know, it's essentially the same. But if there are more objects, maybe the cashier will take more. So there are various ways to model that, in other words. But in general, it's not true that if you store something which is half the size of an object, it will take you half the time. Even in the queuing model and in the bandwidth, you're there taking this place, whether you're served 10 minutes or half an hour.
Any more questions? Okay. So we have arranged refreshments at Coffee Hut. Feel free to continue your discussions there while having a cup of tea. Thank you everyone and have a great evening. Thanks a lot.